Hi, my name is Romil Audhkhasi, and today I will be talking about my work with Professor Michelle Povinelli at the University of Southern California. The subject of our work is efficient light trapping in the mid-infrared using gold black phosphorus nanostructured absorbers. In recent years, black phosphorus has received considerable attention in the context of IR photodetectors, primarily because of two main reasons. First, its ease of integration with silicon, and second, its electrically tunable bandgap. As a result, several BP-based diodes and photodetectors have been demonstrated. The figure on the left shows an example of a BP-based diode operating at a wavelength of 633 nanometers. And the figure on the right shows an example of a BP-based photodetector operating at a wavelength of 3.39 microns. In order to have an electrically tunable bandgap, the thickness of black phosphorus must be lower than 50 nanometers. At such small thicknesses, light absorption in the layer is greatly reduced. For example, for a 50 nanometer thick layer of black phosphorus, the single pass absorption of incident light at a wavelength of 4 microns is only about 1%. This means that 99% of the incident light is lost. One can increase absorption in the BP layer by using light trapping structures which confine light inside the layer. In recent years, several BP-based perfect absorbers using light trapping schemes have been demonstrated. However, majority of these have treated BP as a metallic monolayer. For infrared photodetectors, it is much more desirable to consider semiconducting BP thin films. In this work, we propose a nanostructure design to boost absorption in semiconducting BP thin films in the 3 to 5 micron wavelength range. Our absorption enhancement structure consists of a thin layer of black phosphorus of thickness dBp placed on top of a gold back reflector of thickness dAu. A metallic grating of thickness D grating, period A, and metal stripe length L is placed on top of the black phosphorus layer. The entire structure is supported on a glass substrate. We refer to this structure as the metal dielectric nanocavity absorber. The figure at the bottom explains the physical principle behind the functioning of this structure. One can consider a single unit cell of this structure to be comprised of three regions. Regions 2 on the left and right, and region 1 in the middle. In the 3 to 5 micron wavelength range, region 1 supports a transverse magnetic mode. The electric field profile corresponding to this mode is shown by the magenta curve in the figure. On the other hand, regions 2 do not support any propagating modes. As a result, there is an impedance mismatch between regions 1 and 2. The transverse magnetic mode propagating in region 1 undergoes reflection on encountering the waveguide boundaries on the left and right. At a certain wavelength governed by the length of the metal stripe, the forward and backward propagating waves in region 1 interfere constructively to form standing waves. Here we present one particular example of our MDNA with a grating period of 0.6 microns and a black phosphorus layer thickness of 20 nanometers. The metal stripe length is chosen to be 320 nanometers so that the fundamental resonance is at a wavelength of 4 microns. The figure on the right shows the wavelength dependent absorptivity of our MDNA calculated using the FTDT method. The dotted black curve shows the absorptivity of the entire structure, whereas the solid red curve shows the absorptivity only in the black phosphorus layer. There is a difference between these two quantities because of light absorption in the gold grating. For comparison, we also present the single pass absorption through an isolated 20 nanometer thick layer of black phosphorus, as shown by the solid blue line in the figure. By comparing the red and the blue lines, one can observe that our MDNA provides significant absorption enhancement over a single pass through an isolated layer of black phosphorus. Next, we study the dependence of absorptivity on the black phosphorus layer thickness. We keep the grating period fixed at 0.6 microns and vary the black phosphorus layer thickness dBp from 5 to 50 nanometers. For each value of dBp, we vary L from 0.1 to 0.5 microns. The color map on the left shows the variation of the fundamental resonance peak location as a function of L and dBp. For each value of dBp, it is possible to identify a value of L so that the fundamental resonance is at a wavelength of 4 microns. These values of L are indicated by solid green circles in the figure. We simulate these structures and plot the wavelength-dependent absorptivity for a few different layer thicknesses in the figure on the right. One can notice that for different layer thicknesses, the peak stays at about 4 microns as intended. However, the peak height increases as the layer thickness is increased. We quantify the absorption enhancement of our MDNA by calculating the enhancement factor. This is a ratio of the absorption in the black phosphorus layer of our MDNA and the single pass absorption through an isolated black phosphorus layer of the same thickness at a particular wavelength. The figure on the right shows the enhancement factor as a function of dVp at a wavelength of 4 microns, as indicated by the solid blue circles in the figure. For comparison, we also show the conventional light trapping limit of 4n square, which gives a value of 34 for black phosphorus, as indicated by the solid red line in the figure. One can observe that for all layer thicknesses, the enhancement factor for our MDNA stays above the conventional light trapping limit. The figure at the bottom shows the integrated absorption in the black phosphorus layer of our MDNA as a function of layer thickness. One can notice that there is a trade-off between the enhancement factor, which reduces with layer thickness, and the total integrated absorption, which increases with layer thickness. Next, we optimize our MDNA with a black phosphorus layer thickness of 5 nanometers. The length of the metal stripe is kept fixed at the value determined in the previous step. We vary the grating period from 0.3 to 1 micron and plot the wavelength-dependent absorptivity in the black phosphorus layer of our MDNA for a few values of A in the figure on the left. One can observe that as the grating period is reduced, the height of the peak increases. This increase in absorption is accompanied with an increase in the enhancement factor. So by reducing the grating period from 0.6 to 0.3 microns, one can increase the enhancement factor from around 425 to around 561. We also investigate the performance of our MDNA under oblique incidence. We keep the grating period fixed at 0.3 microns, the black phosphorus layer thickness at 5 nanometers, and vary the angle of incidence from 0 to 60 degrees. The figure on the left shows the wavelength-dependent absorptivity in the black phosphorus layer of our MDNA for a few values of the angle of incidence. One can see that as the angle of incidence is changed, the peak remains at around 4 microns. This is true for highly localized modes as those observed in the structure. The figure on the right shows the integrated absorptivity in the black phosphorus layer of our MDNA as a function of the angle of incidence. One can see that this value increases as the angle of incidence is increased. In summary, we have shown that metal insulator metal designs can be used to enhance absorption in BP thin films. The enhancement factor for our MDNA exceeds the conventional 4n square light trapping limit for all layer thicknesses from 5 to 50 nanometers. The absorptivity in our MDNA is robust to the angle of incidence, and the peak location does not change as the angle of incidence is changed. In addition to providing absorption enhancement, our MDNA also provides a convenient way for electrical contact integration. While using in a photodetector, one could use the back reflector as a bottom contact and the top metallic grating as the top contact. Finally, I would like to thank my PhD advisor, Professor Michelle Povinelli, for her support and guidance, and my fellow lab members for their feedback. I would also like to acknowledge the computing resources provided by USC's Center for Advanced Research in Computing and the funding by our sponsors, the Army Research Office. Thank you.